cappuccino, hold the phone. Take me home. Morning coffee, vanilla latte, sift to go. I drink it slow. Morning coffee, cappuccino, hold the phone. Take me home. Sklia-do-do-do, ba-ba-da-ba. Sklia-ba-do-boo-do-do, da-dee-ba-ba-da-do. Skilla-ba-da-ba-do-ba-ba-ba. Skilla-da-do-do-do-do-do. Ba-ba-da-ba-ba-ba. Hey. Morning coffee, vanilla latte, sift to go. I drink it slow. Morning coffee, cappuccino, hold the phone. Take me home. Morning coffee, vanilla latte, sift to go. I drink it slow. Morning coffee, cappuccino, hold the phone. Take me home. Morning coffee, vanilla latte, sift to go. I drink it slow. Morning coffee, cappuccino, hold the phone. Take me home. Morning coffee, vanilla latte, sift to go. I drink it slow. Morning coffee, cappuccino, hold the phone. Take me home. Sklia-do-do-do, ba-ba-da-ba. Sklia-ba-do-boo-do-do, da-dee-ba-ba-da-do. Skilla-ba-da-ba-do-ba-ba.
What up, everybody? Welcome to Coffee Hour with Paul. Again, my name is Paul, and welcome. And is that music not catchy? I swear it's catchy. To me, it's catchy music. But anyway, welcome to a live stream where we are venturing deeper into Article 250 on grounding and bonding. Now, if you are not familiar with who I am, my name is Paul Abernathy, and I'm the CEO and president of Electrical Code Academy Incorporated. And I also serve on Code Making Panel 5. But let me say that anything I say tonight or in the other two parts to this series, part 1 and part 2, absolutely is nothing to be said for the code panel. This is all Paul, okay? So if I'm wrong and you don't like what I say, don't hold them responsible, okay? That's all me. So welcome again to the live stream. It's grounding and bonding is one of those topics I can never get enough of. And we only scratch the surface of grounding and bonding. And so, buckle up. There'll be plenty of more episodes of this, as I told y'all in other videos, that we are gearing up to do more training and more things. So this is just an extension of that, where we're bringing you some more educational training. And again, one of the things that are dear to me is grounding and bonding. Now, I will tell you, this is all out of our grounding and bonding course that is available over on our website. In case you want to deep dive into it a little more and you want to get more illustrations and graphics, obviously, than I'm going to show, then make sure you check it out. Just go over to our website and you'll see it's grounding and bonding. And it is considered the Fast Tracks Purple. That's the one for grounding and bonding. Purple. Why purple? I don't know. There you go. So that's the grounding and bonding. So hopefully you have watched part 1 and part 2. That was the introduction, kind of going over some of the basics, right? Some of the basic elements to grounding and bonding to kind of set the stage for when you start really digging into the National Electrical Code, right? So part 1 and part 2 are definitely what you want to watch before you start really diving into code references and things like that, because that's more theory, more understanding, ground fault current, all those type of things. So, we're going to get right into this, because I do want to be good stewards of your time. It is coffee hour, even though I tend to go longer than an hour. And it is live. So, not R. Kelly. Thank goodness. Welcome. Welcome. Those that are in the chat, please feel free to let me know where you're at, where you're coming from. If you have any questions germane to what we're talking about, feel free to post them. If I don't know, I'll tell you, and I will get you your answer on an upcoming episode. I am most certainly not a know-it-all, and I don't want to be. I learn something new every day. Thank goodness in this profession we can learn something new every day. Now, I've been blessed enough to walk on shoulders of some great people like Charles Miller, Phil Simmons. Been able to be blessed to work with Mike Holt before. And, so through the years, I've been able to be around people and learn from them, the Mark Odys and things like that. So I have truly lived a blessed life in being able to do that. And when I convey the information to you, it's typically based on years of experience. If you ever get an opportunity, okay, to sit in on Code Panel 5, that is for Article 250 and Article 200. If you get a chance to ever come, and these meetings are open to the public. If you ever want to sit on them and just really see some great minds work, Christine Porter and all that just people that are just very sharp and into this, then definitely make sure you catch an episode, or you sign up, or you come to one of the meetings. Now you got to wait now, because we're done, right? It's going to be a while. We're gonna be at least another year and a half before you'll see public inputs come out for the 2026 edition of the National Electrical Code, and then we'll start getting together again. So right now is the time to write all your public inputs down right now, so that you have them all ready when the 2026 development cycle starts, even though most of you probably haven't even seen what's in the 2023. So anyway, let's get into it. I'll go on and get us over to our presentation. And I just want to let you know we do have the code up so we can go look at the code. I'll show you that real quick because I am a huge fan of NFPA's new link. So I'll kind of show you that real quick and kind of let you see what that looks like. So this is a picture, this is link, and I just love it. I use it on my phone, I use it on my desktop. It's well worth the money you pay for the annual membership. Well worth it. Never would jump back. And no, don't want any PDFs anymore. This is all I want. I want link. That's it. So again, I couldn't be a bigger proponent for it. Jason, Texas, welcome. Of course, we got O out there in California. My condolences to you. Condolences to you, O, for that. All right, so let's go on and get into the presentation real quick. All right. So we're jumping into Unit 1. We're starting to work through this. We've done the introduction. We understand grounding and bonding, the basic principles of why we do what we do. So now we're going to kind of jump into some general information and work through that. All right. So what objectives do we have? What are we here to try to achieve? Now, we might not achieve all of these tonight, but there will be a part 4 to this, and we'll keep on going until we get it done. But after we work through this unit, you'll be able to understand, explain the performance requirements, because we have what's called performance and prescriptive requirements. Most of the NEC is prescriptive, but we have some performance requirements that we have to achieve in 250.4A1. So we definitely want to make sure we achieve those. We're going to explain how the performance requirements relate to prescriptive requirements. And then we're going to explain the meaning of objectionable current over grounding conductors. And, you know, the code panel 5, we attempted to give a definition of objectionable current, and we fell short. We couldn't do it. And we tried to do it, and it just didn't work out for us. And so we ended up not doing it. So at the end of the day, we're still left with the information that we had before on objectionable current. So again, we'll try to discuss that a little bit as we move through and explain what it is and what it isn't, that type of thing. We're going to explain proper connections of grounding and bonding equipment. Again, we're going to be talking 250.8 and proper termination and whatnot. And we'll explain the importance of providing clean surfaces for grounding and bonding connections. Again, your reliability of clearing an overcurrent protected device is only as good as your low impedance effective ground fault current path. Remember, we talked about that back in part 1 and part 2. Well, if your connections are poor, you're not wrench tight where you need to be, if your surfaces are not clean, not making good contact, then the chances are you're not going to get the desired effect. Now, if we're talking about grounding and we're talking about connection to earth and all those connections, then we want transients, we want higher power lines to low power lines, we want lightning, surges, all of that to get to the earth where it's intended to go. But when we talk about bonding connections in a building, we want to make sure that we're going to clear an overcurrent device. We want to make sure that we're adequately bonding components together. That's what bonding is, right? So really got to make sure those surfaces are clean. Make sure you wrench tight properly. Make sure you use the proper fittings where necessary, depending on your application. And so we're going to kind of cover all that in this episode. So the first thing we're going to look at is if you've got your National Electrical Code, and I've got mine with me, what we're going to do is pretty much paraphrase a lot to try to cover as much topic as we can. So 250.1, the scope. Now, .1 is the scope of what this article is going to cover. So the scope of what 250 covers is systems, circuits, and equipment that are required, permitted, and not permitted to be grounded. Did you actually know that some systems are required to be grounded? Probably the system you have coming into your house is required to be grounded. But you have other systems that are even permitted to be grounded, like a corner grounded delta. It's not required, but it's permitted to do so. And they got their own characteristics you have to be very aware of when you're dealing with a corner grounded delta. And of course, you have systems that are not permitted to be grounded at all. And when we say grounded, we mean reference point connected to the earth at some point in the system. So you have these three different things you have to think about: requirements, permitted, and then certain applications where it's not permitted to be grounded. Okay. Number two, circuit conductors to be grounded on grounded systems. Which ones? Which ones get grounded? Okay. Which one of the circuit conductors in the number of conductor layout, which one is to be grounded on a specifically required or permitted grounded system? Right. The location of grounding connections. We're going to cut, that's covered in the scope of 250, obviously. Types and sizes of grounding and bonding conductors and electrodes. Y'all are all probably well familiar. If you've been watching me for any time, you know that we talk about grounding electrodes and 250.50. They all get tied together. Then you start getting the list of the electrodes, right? And 250.52, A1, A2, A3, A4, A5, A6, A7, A8. You start getting this list of the different types of electrodes. And then we get the methods of how you connect these electrodes. All that's covered in Article 250, obviously. We also, item number 5, we talk about the methods of grounding and bonding. Interesting is an equipment grounding conductor is there to clear an overcurrent protected device, but it also extends that connection and it gives you that reference to earth and helps stabilize the voltage, especially when you're reading it with meters and things like that. And an equipment grounding conductor can serve double duty, right? It's a bonding, but it also serves a grounding component. And there's certain methods to terminating and all these kind of things that are covered in 250. Conditions under which guards, isolation, or insulation may be substituted for grounding, like a double insulation. Now, before I get too deep into this, I want to tell you a little thing about something. I usually am known for doing little experiments. I did a TikTok experiment for a couple months, realized that was the dumbest platform I've ever been on in my life. And I since personally got off of that as far as me posting on it. But one of the other ones I post on is called Trade Hounds. And it's quite an interesting platform. I posted a picture, and you're not going to be able to see it, but a panel here, which is a remote distribution panel. And I asked anybody if they saw what was wrong in that panel. Grounding and bonding is so fundamental that the green ground screw was in there connecting the neutral to the enclosure, but it's supposed to be isolated. The neutrals are isolated because it's downstream, right? And so very few people mentioned it. I said, I had people saying, oh, there wasn't the right size to the electrode. I don't know how you would even see that. Plus, this is a remote distribution panel. Why would you even say that? There were people that were saying all kinds of things that are not even germane to the question that was presented. Okay, so at times to speculate and kind of go down that rabbit hole. And the biggest issue in this one was they didn't remove the main bonding jumper, which was up in the service, but now they're doing it to a remote distribution panel. That green screw, which would have been the main bonding jumper back at the service equipment, wasn't removed. And so now the neutral is making contact with the metal case. Now, they did run 4 separate conductors. That's good. But they put that green screw in there, and that's going to create objectionable currents, circulating currents, and that is a concern. So I was looking for people to just say, remove the screw. That's sort of what I wanted them to say. Just remove the screw. But it's interesting. So if you're not on Trade Hounds, it's a neat little app. But boy, I like to post a lot of stuff over there. And if you post something that has violations in it, but you're really proud of it, don't be surprised if I screen capture it and use that in a lesson. I'm just saying. Okay. A lot of misnomers when it comes to grounding and bonding. In fact, you can sometimes go overboard and take something that would have been compliant and technically safe and then turn it into an issue because you did too much. And that's notorious with grounding and bonding. You can go too far. So understanding the limitations and understanding it fully is important. And there are people that understand it way, way more than me, okay? So probably hard to see on your screen, but what you've got in front of you is the image that's actually in the National Electrical Code. So it's kind of gives you a walkthrough structure. that starts out at part 1, general, part 2, system grounding, part 3, direct current systems. And it kind of, well, part 2 is that. Part 3 is grounding electrode systems and grounding electrode conductors. But you see how it's kind of all intertwined. Bonding, part 5, encompasses multiple parts, but you see how they're piggybacked on top of each other and then how it can branch off. So this is just a really good pictograph in order to be able to look at in the code. And maybe if you're like an exam person, you're taking an exam, it might lead you to where you might be able to be, whether the question's about equipment grounding, right? And you're thinking, well, if it's equipment grounding, that's part 6, or it's grounding electrodes, that's part 3. And then if you know where to go, it makes it a little easier for you. But this is what you're probably all familiar with, what you see right off the front in your National Electrical Code, okay? I know. So Rancho says you never can get a straight answer when it comes to grounding. Absolutely. So that's the thing about it, is grounding and bonding, if you leave something up to interpretation, a lot of times people will take it way too far. And all you got to do is spend an afternoon on TikTok or Trade Hounds or Instagram and look at some of the stuff, and you'll get a quick education about what people think they can do versus what they can do, okay? All right, so let's look at some definitions, because again, you know me, definitions are vital in order to be able to fully understand everything that we're going through in the National Electrical Code. We have to understand these definitions. So the recent revisions in the NEC, all definitions related to Article 250 have been located to Article 100. The terms are used in more than Article 250. So what does that mean? So Article 100, and if you're not aware of this, in the 2023 National Electrical Code that's already out on link, if you have it, it moves every definition. Used to be some dot twos in specific articles that were germane just to that article. It was the dot 2 section. Got moved into Article 100. So now in the 2023, all the definitions are in Article 100. Okay, so it makes it easy peasy. But there were certain definitions that were germane just to to dot 2 of various sections within the different articles within the NEC. And that meant that that definition was only germane to that specific article. Now, how do things usually get into Article 100 before they made this change in the 2023? How did it get there? Well, anytime a term was used in more than one article, then it would be relocated to Article 100. Okay, so there's something that's very common to multiple articles, same terminology, same definition, then it would be a candidate to be moved, manual of style, moving it over to Article 100. Okay. All right. Let me make sure that everything's showing up on the screen again. No, it's not. So bear with me real quick, folks, while I try to do a little adjustment here so I can get everything on the screen. I want to make sure I get it all for you. Okay. Sorry about that. All right. Next thing we're going to look at is 250.3, applications of other articles. So when you're using the National Electrical Code, all right, and you are starting to get into grounding and bonding, you got to understand that even though Article 250 is very extensive, and it's probably one of the bigger articles in the code, right, and it can be very daunting, but you got to remember there are other applications in other articles of the NEC that you got to think about, right? So 250.3 covers additional grounding and bonding requirements that are found in other articles. The rules of NEC, y'all are all familiar with this, 90.3, right? The rules of NEC chapters 1 through 4 apply generally. So anytime I have something in chapters 1, 2, 3, or 4, and obviously Article 250 is in chapter 2, it's going to apply generally throughout the NEC. It's very broad. But you know what? You've got rules in chapter 5, 6, and 7 that can amend, modify, or supplement the rules in chapters 1 through 7. Let me give you a great example. So we do a lot with grounding and bonding in Article 250, but you remember there's rules that we have, let's say in 517.13a and b for a healthcare facility. That's got its own rules about redundancy. and it talks about having the armor or the raceway itself qualifying as an equipment ground if you're in a patient care space. But then you also have an insulated equipment ground. Now, Chapter 2 says equipment grounds can be what? Bare, covered, or insulated. But you have a specific requirement that is modifying it in 517.13a and b. And so that's a great example. Another example would be Article 680, and let's say Section 26 for equipotential bonding. So you've got our rules in Article 250 that we have to follow, but then you get up into 680, and guess what? It's going to modify or it's going to supplement something that was in Chapter 2, but now you're up in Chapter 6, and it's going to modify or supplement it. And that's what the code can do. And that is all found in the code in 90.3. And I think so many people fail to go look and see that structure. And just remember, 1 through 4 chapters in the code, broadly. 5, 6, and 7 modify and supplement anything in chapters 1 through 7. Of course, you got 8 that stands alone, which makes reference to anything in the other chapters. And if it makes reference, it's applicable. But 8 is standalone. And of course, then you've got tables and all this kind of stuff, which again are referenced by other parts of the code, which makes them applicable as well. So again, learning the structure of 90.3 is so important. I know it's not part of grounding and bonding per se, but do me a favor. Take a moment and learn 90.3. It's going to help you understand what's happening in 5, 6, and 7 and things like that when you're used to what you normally prepare for in chapters 1 through 4. Okay. Examples of such additional rules, different methods permitted for equipment grounding conductors in 250.118. 250.118 gives you the list of different types of things that qualify as equipment grounding conductors. Okay. So you'll get this list, and that's a chapter 3. Okay. So a good example here is you've got the different wiring methods. Some of them qualify as equipment grounding conductors, that and whatnot in chapter 3. And they'll have their own rules, but then you've got the rules in Article 250. So they intermix between each other. Okay. So again, I should mention I'm not doing Q&A tonight for things that aren't germane to what we're talking about too much, because again, I've only got an hour. And but you can always email me your questions at paulabernathy.com. I have an online portal that allows you to ask me any question you want, and I will get to them, and it could result in an actual live session, a live podcast, or not a live podcast, a recorded podcast. Okay. I have a lot of slides too, guys, so I'm going to try to move through them. But if I got time at the end, I'll try to answer some questions. But remember, you can always send them to me. All right. 250.4, general requirements for grounding and bonding. The prescriptive methods contained in Article 250 are to be followed to comply with the performance requirements of this section. What does that mean? So you're going to have things in this code that's going to tell you do this, do that, connect this, connect that. It's kind of like looking at a pill bottle. Take this pill 2 times a week, 3 times a week. We're going to give you prescriptive methods typically in the code, but we're doing it to do what? To meet a performance goal, right? A performance goal. So what's the performance goal? Well, 250.4A1 is an example of a performance goal. Okay, so what does that say? Well, 250.4A1 it requires grounded electrical systems to be connected to earth in a manner that will limit the voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines. It also states a purpose of the grounding connection is to stabilize the voltage, the system voltage to earth during normal operation. So if you do what the code tells you to do, then you're going to get the performance that's desired and explained in 250.4A1. So as you go through 250, it's going to tell you things you need to do. Those are called prescriptive methods with a goal to meet the performance goal of Article 250. Okay? And ultimately, we have Article 90. It ultimately tells us the scope of what it's intended to achieve with the National Electrical Code. okay? To safeguard and preserve buildings, property, life, all those type of things is the overriding mission of the National Electrical Code. All right, so let's look right here. 250.4, general requirements for grounding and bonding. So as you can see what we've got going on, let me make sure this is showing up okay on my stream. Okay, looks fine. We can work with it. As, again, I'm a little bit big, so let me see if I can't. I'm gonna have to go a little smaller here, folks. There we go. All right, so I might be able, I'm not sure if I can trim it in. Let me do my best here to trim it. No, that's not gonna change the size of it, folks. So anyway, best you can do. Hopefully you got a big screen and you can see it. That's the best we're gonna get it tonight. All right. So as you can see here, here's our transformer. This is utility. Here's the connection to earth right here. So we have a grounded system. The grounded conductor comes in. All right. So you've got your service equipment here, feeding downstream remote distribution panel. Here it's had a breaker that's feeding a transformer. And of course you have a primary, you have a secondary, and of course you have panel downstream from the secondary of this transformer. But notice something here. The whole concept we're trying to do is be able to clear overcurrent protected devices. We've got this reference right here to earth. If we get a fault right here, it goes over onto the metal and cabinet, comes back over here, goes back on the neutral. Okay, there you go. You've got a fault downstream here, gets to the metal enclosure, goes back, follows its way back to the source, clears this overcurrent protected device. Here, if you have a fault downstream right here, this is equipment grounding conductor that's taken to the transformer, okay? And here, even if a neutral, you wouldn't have a neutral here on the primary, you still got to take an equipment ground. You got to clear an overcurrent device, right? So you take it right here, there's a fault right here, gets on the equipment ground, comes back here and clears the overcurrent device. And then you have here, you've got the secondary, and you have the secondary, you have a fault right here. And it all comes back to the source and allows the overcurrent device to trip here. The whole system works. And we're going to look at the pieces. But proper bonding, proper ground, doing everything properly. Notice how this right here is isolated. Notice how the neutral is isolated over here and this equipment ground is connected to the cabinet. This is where they messed up in search hounds, okay? Just so you know, okay? All right. 250.4a grounded systems, 250.4a, and hopefully you're following along in your code book if you have your code book handy. 250.4a grounded systems provides performance rules for grounded systems. So if you have a grounded system intentionally connected to earth, then 250.4a is going to give us some performance requirements. And if you have an ungrounded system, okay, then you're going to have 250.4b is going to have performance rules that you have to follow in ungrounded systems. Okay, so kind of keep that in mind. 250.4a is the performance. By following Article 250's prescriptive requirements, you're going to meet the performance, what we expect you to achieve in 250.4a when it comes to grounded systems, which is probably what most of y'all deal with. But again, we're going to have rules for ungrounded systems, and if you follow those prescriptive rules, then you will meet the performance, what we expect to achieve, okay, in 250.4b. So let's look at it. So first of all, 250.4a1, these again are our performance goals. And let's see if I can, bear with me, I'll try to adjust again as we go. So here's our performance goals. Electrical systems that are grounded are required. Okay, so remember what we said. We have some grounded systems that are required to be grounded, some that are permitted to be grounded, and some that are not to be grounded. If it's established that we have electrical systems that are grounded or that is required to be grounded, then they are grounded, are required to be connected to earth in a way that will limit the voltage imposed by, and you saw me read these earlier, lightning. Okay, lightning strikes the system, it's trying to get to earth. Line surges, you might have a high power line, again, that might come in off a surge upstream on the high power lines. Okay, it's trying to stay in their system. Doesn't need to come in our system, needs to stay in their system. You have unintentional contact with high voltage lines. So your low power lines, we say low, but your service drops during a storm could have an issue where the high powered lines, say 7,200, where it might drop down to 120, 240, might cause those lines to come in contact. That's unintentional contact with a higher voltage line. Okay, could come during a storm, a natural disaster, or something like that. Or somebody could be cutting trees or doing something and make it happen. And then, of course, stabilizing the voltage of the system to Earth during normal operations so that our meters work properly. So when we make one connection from one of the phases to ground, we get an accurate reading, those type of things, okay? So this is an example, and of course, good timing. This is an example of a utility transformer. Here's 7.2 kV, might be running down through your neighborhood, right? And might be what's coming around, and it's going to hit a transformer. Now it's going to drop down to your house. This is typically what you would see, and it's typically how it would look if you're running this type of system. And here you've got your two-phase conductors and your grounded. In this case, it is a neutral, right? Because the here to here and here to here are neutral. Okay, 120 here, 120 here, 240 between them. So this is a neutral system. And so here you see if you have an overvoltage that takes place, whether it's surge, whether it's lightning, whatever it might be, then you see that it's coming here and it gets over and dissipates itself to the earth. Okay, this right here would be a system bonding jumper. Okay, and it gets down to earth and gets to where it needs to be, and everything's happy. You don't have no problem. We don't have anything that's going to be imposed into our electrical system that's going to be riskful to us if this is all done correctly. Okay, so that's kind of what we're trying to achieve here. And so again, me and you as electricians, yeah, we don't deal with this. Now, downstream transformers that are premise transformers, we got to know what we're doing, right? We got to know about system bonding jumpers. We got to know about all those things. But utility, okay, typically we don't have anything to do with that up there. So we got to hope they know what they're doing. All right, so here are examples of grounding systems where these are grounded. So here's a typical one like we might see here, right? So you have a transformer, kind of like that one you saw, 7200. And here we have the secondary utility based now for these. Keep us focused on this. So here you go. This is a grounded conductor. Now, you don't always have a grounded conductor. I mean, you don't always have a neutral. But anytime you have one of the conductors connected directly to the earth, then you do have a grounded conductor, okay? So, and it's not through any impedance device, so it's not in high impedance ground. It's directly to a connection to earth. So this would be through, a grounding electrode conductor to an electrode. So in this case right here, there's a connection. So this is the grounded conductor. But check this out. So this is a delta high leg, and here's a center tap winding from A to C. And this is how we achieve the 120 and 240. Doesn't show the 240 here, but that's how you would achieve it. And of course, any connection from B leg to this neutral point vectorially is going to give you 208 volts, okay? But it's still a grounded conductor because any one of these phases to this grounded conductor is going to give you 120, okay? That type of scenario. Any one of these, all right? Well, take that back. This is still a grounded conductor on this system. Okay, on this system. Because, yeah, if I make this connection here to here, then nah, it's not. Okay, but any of the others, phase to ground, phase to grounded. So this is a grounded. This is typically what you're going to drop if it was a drop down off to your utility. Same thing over here, but this is a Y. So in this Y, people ask why you would use, I get this question a lot, why would you use a delta over a Y? Why would they? You can get more deltas. Let's say it's not this 12208 delta, but say it's a 240 volt delta or whatnot. You can get more phase-to-phase loads out of it. So you might have less lighting loads, less receptacle loads. But a lot of times when you have a lot of the office buildings that's going to have a lot of 120 volt loads, they like to use the Y because you have a lot more ability to get 120 volt loads. It's irrelevant to our conversation. Each one of these, depending on this leg of what's leaving to your premise, is going to be a grounded conductor, okay? Now, whether it's a neutral, this is not a neutral, because of the B leg, but it is a grounded conductor because it's intentionally grounded. Okay, that's what I say. You might have a neutral, but if you make an intentional connection to earth, it's always going to be a grounded conductor. Might not always be a neutral, though. All right. So 250.4A2, grounding of electrical equipment. Quote from the code 250.4A2, it says, normally non-current conductive materials enclosing electrical conductors or equipment or forming part of such equipment, that would be like the cabinets, the enclosures, the raceways, all of that, are required to be connected to earth to limit the voltage to ground on these materials. So bonding, tying all metal parts together, keeping everything done, just being careful here, because I want to show you something. This right here, now this is where a lot of people say, well, wait a minute. You mean I can connect this neutral on the supply side to the metal enclosures and everything upstream? Absolutely. Code allows for it. But here's your transformer. And let's say this is a utility transformer, okay, which they're going to use what's called a multi-grounded systems, means every so many feet, like 200 feet or whatever it may be, they're going to be making their connection to earth along the transformer setup. And here it's dropping down to your house, okay? This is your house. And here you've got the transformer's got a connection to earth out at the transformer. And this is kind of depicting this dashed line, means that there are other nodes on the system that are connected to earth, because that's called a multi-grounded system, multiple points. And then here's our service. So in our service, you've got your grounding electrode conductor, which we have to have. We have to have the grounding electrode conductor going to an electrode. So we have to have electrode. And you'll notice that this conductor right here, this is the main bonding jumper. Now, a lot of times, this can all be depicted on one bus bar. Okay, you could have just had this one bus bar, put this green screw on this. But Phil, who does these graphics, likes to separate stuff when we show it, because it can be used for many different explanations. So he separates it. So this green screw right here is not being used as the main bonding jumper. It's a bonding jumper, but this is the main bonding jumper because this is connecting the grounded conductor to the equipment grounds at the service equipment. So just don't be fooled by this. This green screw could be over here and it could be just one bus. Okay, we're not talking about a remote distribution panel here, folks. A subby, bruh. We're talking about the service equipment right here. Okay, now by doing this, everything's tied together. Everything's at the same potential. Okay, and as long as you put everything at the same potential, you are going to try to an effort to reduce the touch potential across the non-current carrying components of the system. Okay. All right, so 250.4A2, a shock or electrocutional hazard can occur if there is a break in the ground fault current path. Now, we've probably seen an illustration of this before, but this kind of illustrates what happens and why we have to do what we do prescriptively through the code. Why we make sure that things are wrench tight. Why we make sure that we run things the way we do, why we make sure our couplings are done right, and all this type of stuff. Okay, you're only as good as your last, well, I say, you're only as good as your last lock nut. You know what I'm saying? So if you look here, here's a 48277 volt system, and here's a, looks like, branch circuits going out. There's a fault on this end. Now, they're using the EMT. I'm going to assume this is EMT, although I don't see a connector, so it's probably rigid. But it's using it as the equipment grounding conductor. Okay, well, 250.118 says it's okay to do it, so I'm do it. So they didn't run a wire type equipment ground in there. I mean, I know that some people will cringe at that, but code says you can. And so there's a fault right here. So as that fault current tries to get back and has a low impedance affected ground fault current path, well, in this case, it's hindered because of a loose connection. So all of this just stays energized. So basically it stops right here. Here's your ground reference right here because everything is bonded here back to the source, but it's loose right here at where it says loose connection. So I'm measuring between the box, which is connected to ground, and this raceway, which is basically floating. I'm measuring voltage across it. And I am going to have current measure crossing depending on how well this connection is or isn't, because you could see arcing right here. And if this is near combustible material, well, heaven forbid. Heaven forbid. So that's why when you go into like hazardous locations, we have so many other rules you have to follow, right? In Article 500, 501, 502, 503, because that arc, a loose connection, could be catastrophic, right? So again, most engineers will want you to pull, and most electricians will want to pull a wire type equipment ground in there. But I just, 250.118, when we get there, eventually in this series, make sure you're subscribing. We can't learn it all in one night, folks. We got to have a little fun with this. So, and I get to sit with you and have this time together. So anyway, if this lock nut was done properly, adequately, then it should have, at the fault, it would have cleared that overcurrent device very quickly. This is probably an inverse time breaker. So the more the current, the quicker the trip, okay? Inversely proportional, right? So important. But because of that loose connection, this can sit here waiting. And that's the thing about electricity, right? When electricians install something and they say it works, or they do something that's a violation, electricity still tries to work. It just works. But it's sitting there, sleeping, waiting for somebody to come in contact with it and complete that circuit. Then we got a problem. So this could all just remain energized and it wouldn't have cleared the breaker. So, scary thought. Make sure you make those connections. All right. 250.4A3, and I encourage you to follow along because I am paraphrasing, so I want to make sure that you're following along. Normally, non-current conductive materials enclosing electrical conductors or equipment or forming parts of such equipment are required to be connected together and to the electrical supply source in a manner that establishes an effective ground fault current path. Right, so couplings, whether it's compression, whether it's set screw, whether it's whether you're connectors connecting to enclosures, whether you're using the lock nuts, whatever you're doing, we need to make sure that we're going to establish the whole concept of bonding electrical equipment is to make sure that we have that effective ground fault current path. Reliability, clearing that overcurrent device, or at least bonding the components together to reduce touch potentials on certain things. So again, as you start getting further down the system, the touch potential thing starts to go away a little bit. But again, closer you are to the equipment, switch gear, things like that. So it's just vital that you make sure that all these connections are adequate. And in fact, of anything, I tell electricians all the time, especially guys that run projects or gals that run projects and you have a bunch of helpers, make it part of your protocol to check behind them. Not that you don't trust them, but when you're relying on these things, it's so vital that you make sure that these things are done properly, especially if you're going to use a raceway as the ground fault current path. All right, so 250.4A3, bonding of electrical equipment. In its simplest form, what does bonding mean? Bonding completes a path through which current can flow, tying metal parts together so current can flow freely, right? It also helps connect parts at the same potential. We've kind of gone over that. And it eliminates the shock hazard. It eliminates it. I will venture to say that it's only as good as those connections. So it's going to eliminate it. Say this example right here. Everything's bonded properly. If you touch here and you touch here, you're not going to feel a shock. If everything's done right. If you have a poor connection, something happens, you could have it. To eliminate the shock hazard that you deal with this isolated system like this, making sure everything is bonded back in case something gets on the metal enclosure that's not supposed to, then we're going to clear that breaker, okay? All right, so now, with that said, a little bit more dicey upstream, right? Because as an electrician, you know that you don't know whether or not there's a fuse at the transformer. You know there's probably one on the primary side, but it's nothing that you and I have to do with. So the real issue for us on the supply side and all that bonding we do and all that connection that permits us to connect to the grounded neutral conductor and all that, that is more or less for potential, okay? And it does help reduce the shock hazard. Sadly, we're probably not going to clear any overcurrent device upstream. But as many people will tell you, a lot of times those service drops and things like that are just fuses. because we all know the utility doesn't require theirs to be as large as what we would run, right? We all know that. So the real issue here is putting everything at the same potential, and it helps reduce the shock hazard as a result of that. Now, you notice in this illustration here, we have two services grouped in the same location, okay? We've got our ungrounded hot conductors, and we've got our grounded conductor comes down into a wireway. And then, of course, you have these. These are not, obviously, y'all know this. These aren't feeder taps. They are taps. You're permitted to tap service conductors. In fact, we have rules in the code in 230.82 what can be on the supply side of a service disconnect, okay? Which at some point we'll probably get to that. As y'all all know, my new studio opens up in February of 2023, and I have got a slate of great stuff to come. But we got more stuff coming here in 2022. So don't worry, we got you covered with some service stuff coming up in the future. All right, so here's an example. You see some, I love illustrations, and Phil does these really well. So right here, here's your service raceway coming in. So you got to do something that's kind of like an assured bonding, a little extra bonding, 250.90 and 250.92. You know, if you have impaired KOs and things like that, you got to do a little bit more. Okay, well, here you've got a bond right here. So this is a supply side bonding jumper. You're bonding this raceway and everything to the grounded conductor. It's permitted in the code, okay? And then, of course, here you'd have an allowance to have your grounding electroconductor at multiple options and 250.64, I think. So you have multiple ways to do it. I could have come out of each one of these individual service disconnects, but here you can do it on the supply side at one common location. So that's what they're doing here. And then, of course, you see that these are taps that come off, and these are sized, again, based on whatever the loads are here, right? And here you see here, more supply side, because this is a raceway that's on the supply side, okay, of the service disconnect. So, again, that would be an example of a supply side bonding jumper, okay? And then, of course, you got two right here. This is the main bonding jumper connecting what? The enclosure to the actual grounded conductor. Also connecting any, in this case, it shows like a jumper, but could have been a green screw in there. Could have been fine, right? And then this one right here, this is obviously on the load side. So that is called an equipment bonding jumper because it's on the load side of the service. Where do you find all these things at? Well, get fluent, because what you've got is supply side bonding jumpers, 250.102C, and you got load side equipment bonding jumpers, 250.102D, okay? Main bonding jumpers, 250.102C, okay? All those good stuff that we have in the code. Don't worry, we're gonna cover all that kind of stuff. All right, bonding jumpers. We have a myriad of jumpers, and we lump everything into bonding jumpers, but they have specific duties. We have main bonding jumpers, we have system bonding jumpers. Typically, you'll see system bonding jumpers on separately derived systems, like a generator, if it's truly separately derived, a transformer, which is separately derived. You'll see system bonding jumpers. The main bonding jumper is what you're going to see in your main service equipment, main service switchgear, things like that. You'll have what's called a main bonding jumper. It intimately connects the grounded conductor with the equipment grounds, and it gives a location for the grounding electroconductor to make a connection. Okay, and there are some allowances in there, and we'll cover that when we get there, but that's the general gist of it. Now, main bonding jumper and system bonding jumper perform the same function, right? Allow that current to get back to the source to clear an overcurrent device, whether it's a transformer, whether it's a generator, whether it's a utility. It allows that fault current to get back, okay, complete the circuit, and allows it to have a low impedance path, so it allows that fault current to skyrocket. And what happens to the breaker when that happens? It clicks quick, and that's what we're trying to achieve. Now, you have supply side bonding jumpers. They're on the supply side of a service. But you also have supply side bonding jumpers on the supply side of the separately derived system that might be going from the transformer secondary up to the service equipment. I mean, not service equipment, excuse me. Going from the secondary side of the transformer up to the remote distribution panel on the secondary of that transformer. You could have what's called a supply side bonding jumper there as well, okay? You have equipment bonding jumpers. We just saw a picture of that. That's on the load side of the service. And then you have bonding jumpers to metal piping systems and to structural metal frames. We have bonding jumpers that are simply tying systems together, okay? From one piping system to another piping system. From the metal frame of a building Okay, all these type of things, those would be bonding jumpers. So you got main bonding, system bonding, supply side, equipment bonding jumpers, and then bonding jumpers in general that can tie things together. Okay. Now, bonding jumpers, when is a bonding jumper required? That's another question I get quite a bit. Now, when you're looking at services, for example, and you're looking at 250.90 and 250.92, it becomes very evident when you would need a bonding jumper. But let's just look at some instances where bonding jumpers would be critically important to that what? Establishing that effective low impedance ground fault current path and keep the system intact, okay? And loose lock nut connections, okay? I don't know. If you're making connection with lock nut and the concentric, eccentric are so gnarly up, it's so knocked up, or the lock nut is so jacked up or whatever, then chances are you're going to need to put a bonding jumper on that. Another, because you cannot rely on the connection from that lock nut. Okay? That's very broad, but we'll go on and say that. For conduit or cable connections to painted enclosures. So I might have a raceway that's making connection to a painted enclosure, and maybe for some reason, based on where it's located or what the application may be, that I cannot bond that raceway, especially if I'm using that raceway as an equipment ground, then I need to make the connection over from the bus over to that conduit or cable fitting as it comes through, the threaded portion. So I need to maybe put a bonding bushing on there and make that connection. So I need a bonding jumper in order to fluidity of that connection, because I'm not going to rely on that connection to the actual painted cabinet or enclosure. Now, you'll see later we could scrape all that off, and if you can ensure that connection, okay, perfectly fine for feeders, but it gets a little dicey when it comes to services. But don't worry, we're going to get there. I don't know what part of this series we'll get there, but trust me, we're going to get to the nitty-gritty of service bonding and things like that. Service equipment enclosures, again, bonding jumpers if you are running it, because you have a little more assured than normal. Okay, so if you have any concentric or eccentric knockouts or anything that looks impaired and it's got service conductors coming in, then you are going to need a bonding jumper. Okay. Around KO reducing washers, if it's a suspect connection, then you're going, if you don't believe that that reducing washer is going to be an adequate connection, then again, bonding jumpers may be necessary around that. If that connection is suspect, somebody beat to death that washer, that reducing washer. And now, one thing about reducing washers is typically, if you're going to use it to go from a larger size raceway hole opening down to a smaller size, you need to remove all the knockouts, because those reducing washers are designed to fit in there. They're not designed to fit by you just remove one of the KOs. Okay, so usually you remove them all, but check your manufacturer with that. But that's typically how they work. So if somebody's installed it improperly and you're like, it really is suspect, you might need a bonding jumper around it. Hazardous classified locations, again, are heavily going to require bonding jumpers. Again, like we talked about earlier, we're not going to rely on potential loose connections that could create an arc, things like that. And then, of course, anytime you're dealing with over 250 volts to ground, in the code, we're going to be requiring certain aspects where bonding jumpers are going to be required for that as well. Of course, there are some nuances of that. You have things like bonding wedges if you remove all the KOs, or you might have a box that's already rated for like over 250 volts. Then you have some allowances there, but we're just kind of talking in general. These are instances where if you had any of these situations, then a bonding jumper would be required. All right, 250.4A4. Bonding of electrically conductive material, normally non-current carrying conductive material that are likely to become energized, are required to be connected together and to an electrical supply source to form an effective ground fault current path. This is an example where people ask me about gas lines. So you have 250.104 in the code, and they say, do I have to bond the gas line? Well, typically you don't have to bond the gas line. And then we're not talking about CSST and the rules that you have for that. Just gas line in general. You're not going to bond it unless it's what? It's likely to become energized. Now, 250.104 gives us allowances. If I'm bringing a branch circuit to a piece of equipment that mutually has a gas line and my power running to it, and I run an equipment ground, well, I can use that equipment ground to bond and make that connection without doing anything special. And that's in 250.104. But what we're trying to say here is you could have something that who determines what is likely to become energized? Well, I can tell you this. If I've got a piece of equipment and I've got both a gas line running to it and I got an electric line running to it, there's a high probability that because how they merge together, that there is a likely to become energized. The good news is 250.104 gives us some provisions for that. But this is kind of where people will kind of reach beyond this and go, sometimes inspectors will go, well, that's likely to become energized. I'm going to need you to bond it, okay? The issue that you've got to identify, is it really likely to become energized? And you're going to have to work with the HJ on that. I can tell you right now, I've had people contact me because MC cable is within a couple inches of metal frame, and they want the daggone thing bonded because they say that that MC could come energized and then touch that metal. So it's likely. And I would say that is highly unlikely if it's not touching now and you've secured and supported your MC cable in accordance with 330.30. But that's just the things you got to deal with, okay? All right, 250.4A5. Now remember, we're still in the performance rules here. If we do everything we're supposed to prescriptively, we're going to meet all this, no problem. Just do what the code tells us and we'll meet these. But this is why we're doing it. 250.4A5, effective ground fault current path. Electrical equipment and other electrically conductive materials likely to become energized, there's that term again, to be connected or bonded in a manner that is, 1, reliable. Number 2, provide a circuit of low impedance, means we have to construct an effective ground fault current path. Not just a ground fault current path, an effective ground fault current path. One that we intentionally create, okay? Number 3, the conductor must be capable of safely carrying the maximum ground fault current likely to be imposed on it. And I can tell you right now, if we're doing things like equipment grounded conductors, we're basing those on the size of the overcurrent device. We're going to go to 250.122. And if we do parallel runs, we're going to be full-sized equipment ground based on the overcurrent device in all raceways. We're going to have a conductor that is capable of safely carrying the maximum ground fault current imposed on it. Clear that breaker, okay? The earth is not considered an effective ground fault current path. I just got somebody the other day post something right before I ditched TikTok. We were talking about post lights in a parking garage. And a parking lot. And he swore that you didn't need an equipment ground there because driving a ground rod would be effective. And I said, that is impossible. He says, oh, I've seen it happen. I'm like, it's not going to happen. If you don't have an equipment grounded conductor run and you simply take it and drive it in the earth's resistance is just too high. Now, is it probable if the panel was sitting right next to the pole and the ground rod was right next to the panel and right next to the electrode for that panel and it was all right there? Maybe, depending on your soil conditions where you're at. But if you do the math, if you get 25 ohms in a perfect world for ground rods and you have 120 volts, you're only going to get about 4.8 amps if you use Ohm's law. Is 4.8 amps going to clear a 15 amp overcurrent device? No way. Never happen. Never happen. So it's a fallacy to think that way. So I told him, I said, well, you can do what you want, boo. But at the end of the day, somebody gets hurt, they're going to be calling me, and I'm going to come out there and I'm going to hang you. I'm just saying. All right. Next, effective ground fault, metal conduit becomes current carrying conductor when returning fault current to the source. Absolutely it does. So if I have this EMT, as you see right here, and there's a fault onto it, it is going to be a current carrying conductor. Although, don't let that confuse you. It is not to be counted as a current carrying conductor when we're doing things like the number of current carrying conductors and adjustments and corrections and all that kind of stuff. But in a fault condition, ground fault condition, it will obviously carry current. Now, what happens is typically, in this case, in the illustration, you see that it looks like it is using the raceway as an equipment grounded conductor. And 250.118 allows me to do this. Okay. But if you have a wire type equipment ground in there and it's bonded to this box properly, because there are splices here, so it's bonded to the box, then chances are if the raceway or the box is energized, then you've got that wire type low impedance. You don't have to worry about somebody having a loose fitting, a loose connection, somebody didn't tighten the set screw. But I'm going to tell you, in a fault condition, if it is a loose screw or a loose set screw, it's probably going to fuse and it still probably would clear the overcurrent device. But a lot of engineers don't want to run that risk. They're just like, nah, just put the wire in. I don't want to risk it, okay? But I just want you to know that in a ground fault condition, and you're using the raceway as the equipment grounded conductor, it's going to carry current. Obviously, you're going to become a current conductor when it returns that fault current. And then hopefully it clears and then it opens it up, okay? A single loose lock nut or loose or broken fitting can result in a break in fault current. Absolutely. I'm going to tell you right now, fittings, die cast fittings. If you don't put some things in with care and pay attention to what you're doing, they can be the weak link. And again, remember, everything's going to work fine until something happens to that fitting. And then it just sits there waiting. Can you imagine if you have a fault on a raceway and you have a loose coupling and you know they fit loosely, they're not all together tight, but they're loose or it pulls apart just enough. And now they energize this raceway, but it doesn't clear the breaker because they didn't run an equipment ground in there. They're using the raceway. And it sits there until you come up, right? And you grab it and you put them together. Or you grab it and now you've got across your heart. Just for that brief moment, that might be all it takes. Why? Because somebody did not put the fitting on properly. Or maybe it worked loose. I'm a big guy with diligent. I used to really be anal about my connections. But of course, I was the kind of guy, not just because I'm a wire guy, I was always anal about making sure all of my connections, all my fittings, all of my couplings, and everything was done properly. Welcome, Roxanne from Oklahoma, just right up the road from me, about an hour and a half, 2 hours. Well, take that back, maybe 4 hours. I don't know what I was thinking. The casino's about an hour and a half. That's where I leave all my money at the Indian reservation. Let's see. All right, next. Effective ground fault current path. Let's look at some examples here. The ohmic value of a low impedance path not provided in the NEC. So, it doesn't necessarily tell you what constitutes a low impedance path. It just gives you the prescriptive requirements to best achieve it using all of the electrical components, fittings, couplings, lock nuts, proper cable or raceway. It assumes you do everything together in order to do this. And again, one of the best methods, and again, I'm not just stumping of the wire type, and I don't want the people at the Steel Tubing Institute to get all ticked off at me, but when in doubt, run a conductor. And there's something about that extra level. Again, I don't want any upsetness from the steel tube folks. I get it. The code allows it, but I'm just saying, take the wire guy out of me. I just like that redundancy, you get me. All right. Now, one thing you have to remember that what also affects impedance is how you run your conductors, how you run your circuits, not separating them out so you create an expanding, collapsing magnetic field. It creates high impedance when the conductors of a circuit aren't all run together. This can actually create counter EMF, and it can keep these conductors from being a low impedance effective ground fault current path due to that effect. So keep all circuit conductors, including ungrounded, grounded, and equipment ground conductors together. Look at this example right here. So here you've got A, B, and C, let's say, and your grounded neutral conductor and your equipment ground all run through this flexible metal conduit. This is a low impedance path, okay? So you've got the equipment ground, clear the overcurrent device. If the metal flexible conduit, FMC, gets energized. It's connected to a fitting. The fitting is connected to the metal cabinet. There's a good probability here, because of how this is all bonded, that it's going to clear an overcurrent device. Whether or not this qualifies as an equipment grounding conductor or not, there's still that bonding component in how you put things together. You have the greatest chance of clearing the overcurrent device, right? Now, down here, and of course, you don't have any issue of high impedance here because of separating the circuits. Well, down here, this was an improperly devised system. So they needed to run it. So what they did was, instead, they ran two separate cables. Okay, or in this case, I guess it's FMC, so it's conduit. Ran two separate ones. And in this race conduit right here, they put the neutral and they put the black in the equipment ground. And in this one, and they're actually, no, it isn't neutral. Actually, this is one of the phases. So here it's black, red, blue. Here it's black and used the white, and they re-identified it as red, okay? And then down here, they put the blue, which was black, and re-identified it as blue, and then ran the neutral down here. So this is one set of circuits, but separated. And that's going to create a rapidly expanding and collapsing magnetic field. It's going to create a high level of counter EMF. It's going to have a higher impedance than if you ran all of these circuits together. And that is going to have an effect. It creates also something called induced currents. Because of that separation, you're going to have induced. Now, heaven forbid you have any ferrous metal, whether it's the wiring method that's ferrous metal or the cabinet is ferrous metal, and you do this, you create this induced currents, you're going to have induced heating as well. It's something you do not want, okay? You will certainly start melting down insulation, things like that, okay? All right, operating characteristics of overcurrent devices. Talk a little bit about the overcurrent device. So most overcurrent devices, such as circuit breakers and fuses, are inverse time. What is inverse time? Well, this means the greater the current that flows through the overcurrent device, the faster opening will happen. So why do we construct this low impedance effective ground fault current path? Because if you have all this low impedance path, and it's an AC system, so that's why we talk impedance. DC system, we talk resistance. But y'all know that an AC system that talks about impedance is made of inductive reactance, inductive capacitance, and resistance. That's what makes up, you guessed it, impedance. And so differencing between AC versus DC, which is purely the DC resistance. But what happens is, if you construct this path, if you do it right, if you connect everything right, that means that at that fault, it's going to allow that current to skyrocket. And the more it skyrockets, the quicker that breaker is going to react. And that's what we mean by inverse time or inversely proportional. Okay? Manufacturers furnish time curves of overcurrent devices they manufacture. You can get them from your manufacturer. This is real important when you're doing things like selective coordination. We're dealing with healthcare facilities and systems where selective coordination is required. Then you're going to want these trip curves. Now, the good news is most of the manufacturers, if you go with the electrical contractor who is using something like a Schneider or Eaton, they're probably going to develop the entire system. So rather than you worrying about curves, they will usually look at this and tell you the equipment you need. And as long as you install it as they tell you to install it, then you're going to be selectively coordinated. And that's going to save you a lot. Don't let your brain start wandering around a trip curve when the manufacturers will do it for you. Okay? Work smarter, not harder. Thank you, Art, for the donation. Much appreciated. All right, operating characteristics even more here. It says vertical line in the time curve. So the vertical line represents the instantaneous trip current. The curved portion represents the time delay mode of the circuit breaker, like what it's going to take to trip. And then the width of the curve represents the permitted range of the time delay as opposed to the instant trip operation. Okay? So when you start looking at the, here we go. You got the vertical line, the horizontal, and and then you've got the spacing between where the instantaneous, then you have the time delay. All of that is when you're looking at and you're overlaying trip curves. So when I'm looking for selective coordination back in the day, I used to have a big box of manufacturers would supply you with all these trip curves, and I would lay them out and overlap them in order to understand the trip curves and make sure that something was selectively coordinated. And that's before I got smart, right? When I got smart, I just said, let the manufacturers of these equipment do this. Okay, Eaton, for example. You have these smart guys like Tom Dimitrovich, who this is what they'll do for you. Their company will do this for you. Let them do it, okay? Alan Manchi over at Schneider, let them folks do it. That's what they're getting paid for, or their company's getting paid for. After all, you're buying their equipment, right? Okay, but you can get these curves, okay? Time is in seconds on the left axis, so this is in seconds over here. Multiples of rated current at the bottom, so here's multiples of rated current. And every manufacturer can furnish time current curves for their product. But if you let them know what you're trying to do, like I said, this one's from Square D, they will do it for you. Bussmann, yes, has an app as well. Cooper Bussmann, again, I think they're owned by Eaton, I think now, aren't they? So, I mean, they're more than happy to do all that stuff for you. Take advantage of them, okay? Now here you see operation of a fuse, a little different. That's a circuit breaker. So here you see the fuses, times and seconds are on the left. So this is seconds, 0.01, which is, we're familiar with this kind of reference to things like selectively coordinated and whatnot. Then you have what's called the RMS, root mean square, a symmetrical current across the bottom. So there it is here. Okay, this is the RMS. And then 60 amp fuse will clear in about 0.1 seconds for a 400 amp fault. So we're about right here. So this is about somewhere around in here is about 400. Can't really tell, 100, 200, 300, 400 right here. And you can see this. And if you follow this up, okay, then you'll see where's the 60 right here. Right there. So symmetrical in 1,000. So 0.1. 0.1, that's up here, not 0.01, right here. So let's follow it over. So let's see here. So about 400. So 1, 2, 3, 4 right here. Let's follow it up. Hopefully y'all can see my pointer. I forgot to ask anybody if you could see my mouse. So right here, see right here? So right here at 0.01, it's 1,000. But right here at 0.1, you'll see that it's right here. If you count up, 100, 200, 300, 100, 200, 300, 400. Looks like right here, 400 ampere. I don't know what this breakout is. I think it's, I can't even see it with my eyes. My eyes are so blind here. But right about right there. It looks like that's where the 60 would be, right there. So it looks like that must be 1, 2, 3, 4. I don't know. Anyway. Let the manufacturer do it for you. This stuff is confusing as it is, okay? I am no expert. All right. Keep all circuits together. Again, required 250.134.2 and 300.3B1 through B4. Talk about this. Low impedance of fault return path will ensure adequate current will flow, keeping those circuits running together. Rapid operation of the device. And if you want some great information, there's a white paper that's in our grounding and bonding book. Sadly, I can't make that available to you, okay, because you got to have our grounding and bonding course. But it is in there, put out by R.K. Kaufman. It's in the appendix, and it talks about the keeping the circuits together, what happens, the inductive heating, and what happens if you separate them. And it's an interesting read, but it's in there. It's a white paper, and you get it. So if you've got our grounding and bonding series, the purple series, then make sure you check out the appendix and read that. Interesting read. Also, there's the story of the UFO ground in there as well, for those that are in that. All right, 250.4A5, effective ground fault current path. How do we accomplish this? So, the conductor must be capable of safely carrying the maximum current likely to be imposed on it. So, table 250.102C1 is going to talk about sizing things like main bonding jumpers, system bonding jumpers, minimum sizes for grounded conductors, all of that type of thing. That is all what's covered in 251.02C1. And when you get over a certain size, you're going to have to go to a 12.5% rule, okay? Now, table 250.122, that's load side, okay? And that's for things like equipment grounding conductors, and that's based on the size of what? You got it. Size of the overcurrent protected device. Now, the importance here is both whether or not you're doing supply side bonding jumpers, all of those, or whether you're doing equipment grounding conductors on the load side, whatever you're doing, all of those are still going to be a part of an effective ground fault current path, okay? Trying to clear current, okay? Clear that overcurrent device. Now, fault current path through the earth is not permitted as the sole path. So what that means is, yeah, you're going to have multiple connections that might connect to earth, but you cannot rely on that as your return path. It might be there. You might have multiple grounding points on a system, right? Like, for example, I might have a detached structure, and that detached structure's got to have a grounding electrode system, but I'm running a feeder out there. But my service for the house has a grounding electrode system, right? But out there, I've got a feeder running to a remote distribution panel that is going to have a grounding electrode system. But I still have to have that connection with that equipment ground. I'm not going to go through the earth. Even though both of them have ground rods into the earth, absolutely not. Is there multiple paths? Absolutely. But the current is going to travel on the path that provides the lowest level of impedance. Now, you heard that old saying? I'm sure you've heard this, fault current takes the path of least resistance. Well, that is kind of true. It takes all available paths proportional to the path with the least amount of impedance, okay? So that's why we construct a really good low impedance path. The majority of it will travel on that than it will on the high impedance path, okay? But it takes all paths, right? All paths. It doesn't just like go, oh, I don't want to go to you. So some will travel on the earth, but the majority of it's going to travel on that intended, constructed, purposely equipment grounding conductor out to that remote distribution panel. Okay, and that's what's going to clear your overcurrent device. Even though the earth is there and it seems to be in parallel, not going to use the earth as a sole means for doing that. Okay. Fault current will flow over all paths available. We just talked about it. It will go through the earth, but again, the lowest impedance path is going to actually carry the most current. So we understand there'll be other paths. But that lowest impedance path is going to carry the majority of the current. And why is that important? Because that's what we're trying to clear a breaker. That's what we're trying to do, okay? The highest impedance path will obviously carry the lowest amount of current. So the earth, for example, if there was any traveling on earth, it's going to be low. Now, that doesn't work the same for utility folks. Because for the utility folks, they're dealing with a high level of voltage in low fuses, like 2 amp fuses, 3 amp fuses. They can use the earth for their application because they got a really high voltage. Do some Ohm's law and you'll see the difference, okay? So, sit down and do 7,200 volts and 25 ohms for ground rods, and then sit down and do 120 volts with 25 ohm ground rod, and you're going to see the difference. That's why they can do it and we can't, okay? We can't use the earth for that, okay? All right, ungrounded systems, 250.4b, even though the system is not grounded, the enclosure must be grounded and bonded. So what does that mean? So just because we're generating an ungrounded system means we're not taking one of the phases, we're not connecting it to earth, we're not making that intentional connection to earth. That's not going to remove us from doing things like grounding and bonding because we're still going to have overcurrent devices we have to clear, right? So we're just not establishing an intentionally connected to earth ungrounded system. A grounded system. We're creating what's called an ungrounded system, okay? But we still got to remember, we've got bonding rules, we got grounding rules, we got breakers we still got to trip, things like that. So keeping all that in mind. All right, B1, grounding electro equipment. So let's talk about grounding electro equipment. Remember, now we're talking about ungrounded systems here. So this would be the time for you to take a bathroom break if you don't really care about ungrounded systems. It says non-current carrying conductive metal enclosing electrical conductors or equipment or forming part of such equipment are required to be connected to earth in a manner that limits the voltage imposed by lightning or unintentional contact with high voltage lines and limits the voltage to ground. So we still have to take this equipment and connect it to earth. We're just not taking the system and taking a connection to earth, right? So let's look at an example here. So 250.4b1, it says, this is an ungrounded system, okay? Wherever it's being supplied from here, it's coming in, 3 phases, boom, boom, boom. It's coming in, A, B, and C. Now here you see it going downstream, and we get a fault right here. Well, we get a fault right here. The first ground fault on an ungrounded system grounds the system, okay? So in other words, it turns one of the phases. When you get a fault, if there's a phase fault here, what does it do? It turns this system into what? A corner grounded system. It creates and establishes in a ground, okay? And if any, current will flow on that circuit. To clear the overcurrent device in an ungrounded system, at some point you're going to have another phase fault out to the raceway or fault out to the other phase, okay, in order to clear an overcurrent device. This is why systems like this that are ungrounded systems will generally have lighting and little lights and then monitoring or an alarm type of systems and things like that. But the point I want to make here is notice this cabinet. So this has no grounded conductor brought to it, but you notice it still has to be connected to earth, okay? Grounding electrode provides earth connection to ground the system. Why? Because it told us that we had to do that, okay? All right, next, 250.4b2, non-current carrying materials enclosing electrical conductors or equipment, raceways and whatnot, or forming part of such equipment are required to be connected together and to the supply system grounded equipment in a manner that creates a low impedance path for ground fault current that is capable of carrying the maximum fault current likely to be imposed on it. So, interesting thing. Trying to understand the difference between a grounded system and ungrounded system, remove the complexity of having a grounded conductor or a connection to earth. We're just saying get past that. Now we're going downstream of that source. We're still going to have to use raceways and make sure those couplings are done right, those lock nuts are done right, we make all those connections properly. We still got to do all that. So if you remove all of that about the grounded conductor and the connection, if you remove all that, doesn't it sound very similar to what you would do on a grounded system? Sure it does. Now, 250.4b2, bonding of electrical equipment. Second ground fault. So that first ground fault, here was that first one, remember? I kind of gave the beans earlier. I kind of gave it away a little bit. But anyway, I get excited. So the second ground fault right here in this system right here. So a second ground fault on the system. Okay, so the second ground fault on a different location on the ungrounded system. So this is the one that happened here. And then somewhere else, so this one didn't clear right away. Okay. This one down here happened at another location, and this one is in the black. This one happens to be in the red. Okay, so now you've got fault current coming in, right? So current will flow from the source of the first fault. So his fault here comes back through, over this metal path, down through the second fault path, okay? And then by doing that, it'll end up coming back through the red conductor, back over, and then go back, completing the circuit, and then guess what happens? Clear the breaker. So there, a lot of times in these systems, I want to know when this first fault takes place. And that's when you have alarms and lighting. And again, ungrounded systems are their own little unique beast, okay? But those that know them, those that work with them, they get it. They understand how those systems work, okay? 250.4b3, again, we're still doing ungrounded systems, says bonding of electrically conductive material and other enclosures. Remember, these are the what? This is the performance. If you do everything right in the code, you're going to meet the performance of what we're trying to achieve right here. The same as we did for 250.4a, same for b. Okay, that's why the code, that's why 250 is so thick. There's so much to do. That's all prescriptive. But why are we doing it all? We're doing it all to meet this performance rules. That's why we're doing it all. Okay? Yeah, ungrounded systems. The only ungrounded systems, they're rare. They're still out there. They get done all the time. The only ones that I ever dealt with was in a smelting plant. And a smelting plant that I was there as helping them design it as a consultant. The issue with that one was what you didn't want is if that thing was pouring molten metal and it was all electric, if it was pouring molten metal, you didn't want a fault to take place and that thing to shut down in the middle of a pour. They would much rather you have one fault and let that thing finish what it's doing. And then when another phase-to-phase took place that completed it, then what would happen is because the heat that'll build up at that fault, it will happen. Then what happens is then it would clear it. But they wanted to get it in a safe position. So they would have these alarms that go off. Everybody would scramble. They would try to dump whatever they had at that time or stabilize it. And then they would have a crew that would go hunting for that fault so that they didn't get to the point where they had a second situation where it actually did clear the device. Okay, so they had a crew they would immediately spring into action. And I'll never forget it. On that facility, the head electrician was a woman, and she had a pink hard hat, but she was tough as nails. Tough as nails. And when that would happen, they did drills. And she would, I swear you, she looked, I ain't lying, man. She looked petite. Is that petite? She was gorgeous, but she looked petite, right? And we got a lot of women in the trade. But let me tell you what happened. When that alarm would go off and they'd go through those drills, because the smelting plant, I mean, people could get really hurt. Her voice would change. She would start barking out orders. And I was like, you go. She looked like a different person. It's like her head spun around. She was just geared that way. And it was amazing to me. And I laughed at some of the guys. I was like, does she like that? And he goes, oh, yeah, sweetest person in the world. But when that thing goes off or something happens, and she was also the safety coordinator, dude, she would just change into a different gear. And I was like, you go, woman power. Because she was top notch. She had her pink hard hat with her stuff all on her, boy, she could hang with the guys. I ain't telling you what. All right. Bonding of electrically conductive materials and other equipment. Electrically conductive materials that are likely to become energized are required to be bonded to create a permanent, again, fittings, make everything upright, wrench tight, do what you have. It's got to stay there. It's permanent, low impedance path for fault current that will carry a maximum fault current likely to be imposed. When we say maximum fault current, that means you got to know how to do the sizing. You got to know what's involved. Okay, in doing this, and that's why we have the National Electrical Code. Thank goodness that we have the code. Otherwise, we'd be having people out there running 14 gauge to 1,000 amp switchgear. Well, I'm a little exaggerant there, but again, if they thought they could pay less for copper by running something smaller, let's just be thankful we have the NEC. Let's be thankful that we have such great installers out there today that we really care. Unless you're on TikTok or those other platforms. I'm just teasing you, okay? But some things will make you cringe. All right. Next, 250.4B4, path for fault current. Okay, we're still in B. We're still in ungrounded systems. Thank you, JCC, for the donation. I much appreciate it. All right. Low impedance path required from any point on the wiring system. That's why we're tying it all together. That's why we're using proper couplings, proper fittings, wrench tight, proper connections, bonding jumpers where necessary. Providing that low impedance path at any point on the system, if there's a fault condition, then what happens? It facilitates the operation of the overcurrent device, but only when a second fault occurs. In the first fault, we should have some type of monitoring system for these ungrounded systems, right? Again, earth is not permitted to be the sole only equipment grounding conductor. Yes, it might be a redundant path, but again, the resistance is so high, it's not going to do us any good, and you certainly don't want to rely on it. We're not the utility here. We're on the NEC side of acceptance under the scope of what's covered by the NEC, so we don't care about the utility, folks. We're worried about what the NEC says, so we're not going to use the earth. And again, the code reminds us that the earth is not considered an effective ground fault current path. And remember, the code says it has to be a low impedance, effective ground fault current path. We already know that the earth can't be that. So there's no sense in even bringing the earth into the equation, right? All right, let's talk a little bit about objectionable current, 250.6. The term objectionable current, I'm sure y'all have heard that forever, okay? Objectionable current, not defined, so subject to interpretation. Now, we tried to define this, but we fell short of defining it. What is objectionable current? Okay, so equipment grounding conductors are not designed to carry current on a regular basis. So if you were to do an improper case to neutral, all right, so let's just say that picture I showed you on trade hounds, where the main bonding jumper was installed downstream of the service, right? So now it's not a main bonding jumper anymore. It is a jumper, but it's improperly installed. So now the grounded conductor, or the neutral in that case, is making a connection to the enclosure. Well, that's going to give us circulating current. It means it's going to travel in paths that it wasn't intended to be. Because the equipment grounding conductors and all of the metal raceways that you're required to tie together, they're not designed to carry current on a regular basis. But current will be circulating on a neutral conductor all the time. All the time. So we do not want that current traveling on the metal parts. Hang in there with me, Beans Garage. I'm almost done. This is going to be a second part to this one because I realize I've just gone over an hour and a half, and I apologize. I broke my rule. Coffee hour is now turned into coffee marathon. I can't help it. I get to talking. I get to teaching code. I love it. I love this trade, and I love teaching people the code. So if I make an improper case to neutral downstream, where I don't isolate the equipment grounds and the grounded neutrals, then I create example of objectionable current. And that circulating current can cause all kinds of problems, not just a shock hazard, but it also can cause issues with other electronic equipment and things like that. So again, that is kind of an example of objectionable current. And the code tells us that we've got to try to do something to remove that objectionable current. We can start taking some connections loose, but we cannot remove the effective ground fault current path. So we've got to analyze the system very well. Very well. Okay? Now, it says these conductors are often sized on their short time current rating, but I can tell you right now that equipment grounding conductors are sized based on the overcurrent protective device. Now, inherently, overcurrent protective devices usually operate or trip at 6 to 7, depending on what you're dealing with, at their rating. So a 20 amp overcurrent device, typically 20 times 6 or 20 times 7, depending on the manufacturers. Then what happens is it takes that much current to trip it. Well, if you provide this low impedance path properly and you do it, you're not going to have any time, because we're talking about thousands of amps instantaneously. Okay? So, not going to be an issue. I know, look at O. He's like, keep going, you can do it. All right, 250.6a, arrangement to prevent objectionable current. What do we got to do? 250.6a. Now, it says the grounding of electrical systems, circuit conductors, surge arresters, surge protective devices, and conductive, normally non-current carrying parts of equipment, that's the metal cabinets, that's the wireways, metal wire, all that, is required to be installed and arranged in a manner that will prevent objectionable current. A good example of this is downstream anywhere. You do not want to make a connection, okay, of the grounded conductor, or in most of the cases me and you deal with, the neutral conductor. You do not want that making connection in the box or in a cabinet. Now, one of the things that's interesting for everybody that hates AFCIs, arc fault circuit interrupters, we get a lot of things that people refer to as nuisance tripping when you put an AFCI in, and they want to blame the AFCI. And again, it's not without some issues with those devices, but reality is majority of those issues are when people push things back in the box, and now the grounded neutral conductor comes in contact with the equipment ground. Now, that won't necessarily clear an overcurrent device on a standard breaker, okay? Because they both go back to the source, right? They both go back to the same location. So that won't necessarily clear anything. But it could put objectionable currents. It could put current traveling on a path that wasn't intended to be on. So an AFCI can detect this. So that's why I like to refer to AFCIs as diagnostic tools. Whether you like them or not, whether you're a big proponent of them or not, they are diagnostic tools, and I like to think of it as extra insurance for the electrician. I'm just saying. That's a good way to think about it, since you got to dish money out anyway to take care of them. You might as well think of them in a positive way. You with me? Think positive. Everybody knows I'm just always a positive guy. Okay, anyway. So here you go. Let's look at what we're talking about right here. So here's an example. Improper grounding of the neutral past the service. Remember that picture I gave you about that trade hounds image? So here's a classic example of that right here. So you have the service equipment. Here's the neutral coming in. Here's your ungrounded conductors coming in. All right. Here's your neutral going out downstream. Here's your cable or raceway. Doesn't matter. And this right here happens to be the main bonding jumper. Okay. And now, again, remember, this could all be on one bus, and this green screw could have been over here, but Phil likes to separate them so that you understand that the main bonding jumper is used to connect the equipment grounds to the grounded conductor, all to the grounding electrode system, okay, in the service. That's why he likes to do it like that. All right. So here's a case. Check this out. This is a remote distribution panel. And here's your bus. And notice here, the green screw is in it, connecting this neutral to the enclosure. Now we have a separate bus because this raceway is being used, right? And this metal is connected here to here. So we assume this has all been installed properly. But by them putting in this screw right here, now what you've got is normal current that would be traveling on a neutral is going to also be coming back on other paths, okay? All the way back. And what this does is creates, as you notice here, parallel paths. And it also creates objectionable current traveling on unintended paths. And so in that case, you also have to worry about things like how these circuits are run at this point and how they start to separate. And you could get some induced voltage from that. Probably not a lot. But again, these are things that you gotta not do. This is a prime example. This is why you see electricians harp. Make sure on that remote distribution panel, or as Jay likes to call it,
the subby, bruh.
Make sure you remove it. And I posted that on Trade Hounds, and it took forever to somebody to say, oh, remove the green screw. I had somebody said, well, it was probably loose. It's a linear picture. If that green screw's in there, I'm going to assume that sucker's in there. You could get that daggone thing out of there, okay? I don't want to have current circulating on everything, okay? We're almost done. We're almost done. Hang in there with me. All right. 250.6a, arrangement to prevent objectionable current. So check this out. So this one up here, you have the service and you have a second building. Now you notice you have all of these gas lines, water lines, cable trays, cable shields, whatever, and it's mutual between buildings. So these are bonded at the service, right? But downstream, somebody improperly connects them to the neutral conductor. If these types of systems are mutual between the buildings, right? And then what you have now is you have neutral current traveling from the service to the second building, and instead of coming specifically back on the neutral's return path, it's also coming back on what? These other metal components. And this creates an example of objectionable current. Now that's a very hazardous condition because we don't know the integrity of these paths. So if these paths have a loose connection, then you could have something just waiting for an accident to happen. And you might not even know this is taking place. Man, look, this is why we get big bucks, right? This is why we don't make plumber wages. This is why we get electrician wages, because we need to know how these systems are done. And there's so many people that think, oh, I got to bond everything. I got to bond everything. And they take a condition that might have been okay, and then they make it worse, right? But how do you rectify this? Well, look down here. Same scenario. So these assume that these are likely to become energized at the service. So the inspector says you got to bond them. So they're all bonded. But here at the other building, at their mutual systems, say maybe a campus setup or something, notice how the neutral is still isolated. You make these bond connections to the equipment ground, not to the neutral, okay? So they're all bonded. They're all at the same potential. Everything's good. Anything gets energized, it'll go back and clear the overcurrent device. We're fine. But we don't have objectionable currents circulating on paths that they weren't intended to be on. And this is a simple removal of this jumper and instead moving it over to here. Okay? That's just, you know, and also the big problem they have right here, as you can see, is this jumper. Here, that's been removed. Here, it's in there. So the main bonding jumper wasn't removed. So many people get this wrong. I just looked at a couple of houses, third party, where I was asked to do some inspections, I guess about a week ago now. And every panel that I looked in, they do a lot of tract homes. Every panel I looked in there had an objectionable current issue. And it's not because they weren't knowledgeable. It's because nobody ever told them, and they were doing the same thing over and over and over and over and over again. And nobody ever stepped up because they don't get inspections out in the county. Now they know. Okay. Now, 250.6b, alterations to stop objectionable current. So let's say you have an objectionable current condition, maybe one that we just saw. What do you got to do? Well, if the use of multiple grounding connections results in objectionable currents, take one or more of the following actions. Well, I have to analyze what's being done, and I have to disconnect one or more, but not all of the grounding connections. I don't want to lose the integrity of the service, but I might have to look at it that goes downstream. What do I have to do, or what did I do that created my condition? I will start to look at it and maybe move things around. Now, I cannot get rid of my intended path at the service, but I might want to see what I did wrong downstream and start looking at how I fix this. Okay. Now, I could change the locations of the grounding connections. I can look at where I'm at. Maybe it's a multi-story building and I'm doing something. I'm like, well, maybe if I change a location, that'll change my objectionable current condition. So you start to analyze it. The code is telling you, you got to do it. It says interrupt the continuity of a conductor or conductive path interconnecting the grounding connections. Might have to take, now in this example, take this off. Reroute this conductor over here. Get rid of this main bonding jumper because it is a remote distribution panel. And this is a violation of 250.24A5. So that's a procedure I would have done. And then, of course, it says other remedial action that is approved. What does approved mean? Well, that means you're going to have to work very closely with your AHJ. And your AHJ can look at it. And obviously, if there's an objectionable current thing, he's going to have to look, or she are going to have to look at it. Because I know I got Roxanne in the room. She's an inspector. And you have to look at it. I think you're an inspector, Roxanne. I think you are. You have to look at it and go to yourself, okay, can I achieve this remedial action and not make it unsafe, but yet still get rid of the objectionable current? And it might be just a case where a guy or gal just started bonding everything. And remember, grounding and bonding is a situation where you can do too much sometimes. You can go from a good, compliant, safe installation really quickly to an unsafe installation simply by thinking you're doing more. And sometimes with grounding and bonding, more is not best. That's why it's one of the toughest articles to learn. Okay? Now, neutral current can flow over equipment grounding conductors that are connected correctly, where multiple grounding electrode connections are made. So look, you can even make connections downstream. And this is why the code panel 5 struggled with defining objectionable current, because there are some connections that will allow you to do that imposed objectionable currents. And we had to struggle with that. Okay, there's allowances in the code for existing applications for you to use the grounded conductor for things like dryers and ranges that have been around for decades. And we can't do it anymore, but they are allowed. And those connections are permitted, but that goes directly against what we're trying to achieve. So we had a tough time fully defining objectionable current, understanding that there's some applications in the code where you might end up with an objectionable current application. And we just got to bite our tongue and do our best to try to resolve it. The best thing is don't put yourself in that position in the first place. Neutral current will flow over all paths that are available. Absolutely. So if you connect that neutral conductor improperly to something downstream, whether it's in a junction box or whatnot, bootleg grounds happen all the time in order to fool those little 3 lights, and they'll make a connection over to the actual receptacle, over to the neutral, and then they put it to a metal box and it fool that little light. But now what you've done is you've energized that metal box. You've done it. It's just, people don't realize the harm that they can do by just trying to get past the home inspection. You create a hazard, okay? Now, this includes between grounding electrodes to the service and to little utility grounding electrodes. So again, current is going to travel on all paths available. And just remember the old golden rule. All current doesn't take the path of least resistance. It takes all paths proportional to the impedance of that path. If you have a really good low impedance path, you're going to have most of the current travel on that path. And that's what we're charged with constructing. So look at this example. Here's our utility. Here's our service disconnect, and we've broken it all out. So this could be an example of maybe 230.85. This is the service disconnect, an emergency disconnect that's required for a 1 and 2 family dwelling in the 2020 code. Hey, did you know that in the 2023 code, this is also now required? Emergency disconnect is also going to now be required for feeders to dwelling units. Now you do. So that's a change, and I can't remember if it's 225.41 or 42, but subscribe to my Instagram and you'll see a lot of new changes that are coming when it comes to the 2023 code, and I'm sharing them with you. All right, so anyway, here's the service. Now it goes downstream. So here's the service, and it has to have a connection to earth, okay? Now here, the building's main disconnect, connected to earth again. Then the building's disconnect to meet another feeder, connected to earth, and then another one connected to earth. So you've got parallel paths for neutral current created by multiple grounding electrode connections. I remind you that this right here is the importance of this is you'll notice that together here, they're together on one bus, but as they get downstream, they're isolated, okay? But what you need to remember is how this works is that here you've got current going through the system and it's coming back on the neutral, but also is going back to the source utility. But since they got multiple ground points, these could be separate buildings, right? Then what you've got is you'll have current also going back on the equipment grounds to get to earth to come back to the source. So it can travel in all paths, but I can promise you this path, if constructed properly, is going to carry the lion's share of that return current during a fault condition, okay? And that's where you're going to get your overcurrent device cleared, okay? Not the earth. But this is kind of illustrates that it travels on all paths, okay? All right, temporary currents, 250.6c. Temporary currents resulting from accidental conditions such as ground fault. So this is what happens when you know that the raceways are not designed to be current carrying. They're non-current carrying metal parts. But under a fault, when a ground fault occurs, and now we have an accidental condition where ground fault currents is now going to be on this equipment. So these are called temporary currents. They're not objectionable current. They're happening hopefully very briefly, and then a breaker will clear or a fuse will blow. Okay? So you don't want to classify those as objectionable current. We have a hard enough time tackling objectionable current than thinking all these possible fault conditions could be considered objectionable current. They're not. They happen very quickly, and hopefully, if you've done everything right, it'll clear the breaker. So temporary currents resulting from accidental conditions such as a ground fault current that occur only while the grounding conductors are performing their intended protective function to clear a breaker are not classified as objectionable current. So here you go right here. We have a fault to the enclosure right here. It gets back on the enclosure, comes through the raceway. We'll assume this is rigid and it is allowed to be an equipment grounding conductor 250.118, no wire run. It comes back here and it's going back through the enclosure and it gets over here on the main bonding jumper over to the ground and neutral conductor, goes to the source, completes the circuit, and guess what? Clears the overcurrent protective device. Boom, bada bing, bada bang, everything clears, okay? 250.6D, limitations to permissible alterations. All right, okay, so alterations not permitted to isolate electronic equipment from equipment grounding conductor path. Currents that introduce data errors are not classified as objectionable. Now, let me explain something. So sometimes you might have a piece of equipment that will run a raceway to it, and they want it to be isolated away from the equipment, okay? So they don't create noise, right? And that noise is not considered objectionable current, but it can affect how the equipment runs, right? But you still have to run an equipment ground. So don't think that you don't have to do that. And a lot of times, equipment that might generate static electricity, like something with something that moves, like a treadmill on it or something that creates static, a lot of times they'll want something like an auxiliary grounding electrode there at that piece of equipment to dissipate the voltage generated by that piece of equipment's reactionary effect. That is not to take the place of an equipment grounding conductor. That is not to take the place of what we've got to bring to that equipment. That is something that maybe the manufacturer wants you to do. And if they drive a ground rod in the middle of the floor or whatever, that's on them. But that is not to take the place, okay, of it. But you might have an application where you bring a raceway to a piece of electronic equipment and then you put a plastic nipple on it to isolate that raceway from the piece of equipment. Well, if you do that, guess what you got to do? You still got to run an equipment ground to it. You're not going to lose that. You still got to have it. But you're able to isolate the raceway away. Okay? Just some examples. Now, you're not permitted to isolate data processing equipment and connect a local electrode. So in other words, if I had a piece of equipment and they want a clean connection, they can't say, well, I don't want you to run any connection to the system. I don't want an equipment ground. I don't want any connection to anything that might be connected back to that source connection. I want to have my own electrode here. You know what? You drive the electrode if you want. That's an auxiliary. It has no rules you have to follow. It doesn't matter whether they want to run 14 gauge to it. Okay? It's just something that they want. It's in addition. Go for it. But it is not to take the place of the required equipment grounding conductors and all that kind of stuff, okay? All right, now if you did that and you said, well, screw it, because it's data processing and the noise, I'm not gonna run an equipment ground. Well, you know what? You're gonna violate 250.50, 250.110, 250.134, and in doing so, if you were to drive ground rods there and use that only as that source, one, you're not gonna clear overcurrent devices unless you have a short circuit. But secondly, now you've got two different earth potentials. You have the ground rod for that data processing equipment or whatever, and now you've got the raceway that supplied the power there or an equipment ground that came there. So you've got two different potential points because one goes back to the system's connection to earth, and now you've got another connection to earth, creating separation. Not good, okay? So we don't want to do that. Now, it says a remote grounding electrode will usually not carry enough current to operate a 15 amp circuit breaker. We already kind of did this, and then we used the example of a light pole, right? If it's perfect ground rod in a perfect world, 25 ohms, 120 volts, you do the Ohm's law. What do you think the amps are going to be? about 4.8 amps. Is that going to clear a 15 amp breaker? Absolutely not. So driving your ground rod at your data processing equipment because you want it isolated away from the noise that you might get from the electrical system, not going to happen. So what do? You run an individual equipment grounding conductor to it. If you don't want the raceway that may or may not qualify as equipment down, you don't want that physically connected to the equipment. So you run something isolated. Okay, code has provisions for this. But I don't want nobody driving rods around this equipment thinking that's going to take the place of anything, because it's not. Okay? All right, we've talked a lot about it. Now we're going to talk quickly about the connections. 250.8. One of my favorite areas in 250 because it talks about it's where the rubber meets the road. It's where I'm making those connections to grounding electrode conductors, equipment grounding conductors, system bonding jumpers, the actual connections. It says equipment grounding conductors, grounding electrode conductors, bonding jumpers, whether it's main bonding jumpers, system bonding jumpers, supply side bonding jumpers, all of those glorious bonding jumpers must be connected by one or more. So you don't have to just pick one. You can use any of these if you want, and multiples of these if you want, by one or more of the following methods: listed pressure connectors, terminal bars, pressure connectors listed as grounding and bonding equipment, exothermic welding. If you've ever done exothermic welding, that's where they actually have a chemical reaction. A lot of times this is done in like communication towers and things like that. Machine screw type fasteners engaged not less than 2 threads in an enclosure or secured with a nut. So if you've ever looked at the back of your panel enclosure where that green screw goes into it, you're going to notice that it has to engage in at least 2 threads. But again, if it didn't, then you could still use a machine screw, but you're going to end up having to do what? You're going to have to put a nut on the other end to make up for that fact that you don't have the 2 threads. Even though you're using a machine screw, if you're not going to engage 2 full threads, which most of the cabinets that have that green screw or ground screw will give you that, right? But if not, you can still do it. Just you better put a nut on it, okay? Number 6, threaded forming screws that engage not less than 2. So these are screws that make their own threads. They form their own machine screws, okay? And still have to engage at least 2 threads into the enclosure if you're going to use it. Connections that are part of listed assemblies might be part of or integrated into the assembly. And of course, other listed means this is a catch-all because many manufacturers like Burndy make a lot of grounding and bonding products and they get them listed. So this is a catch-all because, again, we might have something that doesn't capture everything in this list, but they might put out something that gets evaluated, it gets a listing, and it's designed for grounding and bonding, and they want to be able to promote it. This list could go on forever because those folks make a lot of stuff, okay? All right, so here's your example. So here are your listed pressure connectors, wire bonding devices. People refer to these as wire nuts. It's a trademark by Ideal, by the way. Here's your terminal bus, okay? And this is what you see in the panels that you're gonna make your connections, your equipment grounds to, and things like that. A pressure connector listed for grounding and bonding. Believe it or not, this is an acorn clamp. Could be a saddle clamp. Those are pressure, means that you have to apply some type of pressure in order to make the mechanism come together. Here's your exothermic welding. It's an actual process, okay, where you use a reactionary process. There you go. There's your machine screw with 2 engaged threads. Here is your thread forming. Notice how it has a taper cut. As you can see the taper. And then as it goes in, it actually cuts the 2 full threads that are engaged. And here's your connections that are part of a listed assembly. That means they're integrated, in this case, into the panel board. There are all these connections here that are part of the manufacturer's assembly. Okay? And they know their stuff, and they provide that for you. And then other listed means got different types of lugs, and again, as a catch-all for other different things that the manufacturers can supply, okay? All right, exothermic weld, use the proper form for conductors and objects. In other words, not all exothermic welding bays are created equal. It is a lot of times relevant to the size of conductors that you're going to be doing so that you get an adequate weld, okay? We don't get a crap weld, we get an adequate weld. The manufacturers will tell you how to do it. If you've never done one of these, at least try to do it once in your career. If you're a resi guy and you've never done this, catch up with a commercial guy and say, dude, can we do one of those? All right. The welding temperature, usually, again, protective. You want to have 4,000 degrees Fahrenheit. Follow safety precautions or procedures, gloves, goggles. Follow the manufacturer's instructions and examine and test the finished weld. Again, make sure you examine it for any cracks, any pore, slagging, or anything. It wasn't done properly. You'll be able to get used to what it looks like when it's done well. And when it's done well, it ain't coming loose, okay? Compression connectors. Suitable for wiring material marked on the shipping carton and connector itself. So if you've got compression connectors, you need to make sure you look at the packaging, because a lot of times these are small, little components, and you need to look at the carton and it'll tell you what it's used for, whether it's aluminum, whether it's good for copper clad aluminum, whether it's good for copper. All those things are going to be in the container. Some of them are pre-filled with oxide inhibitor. Some are not. Okay, misconception, aluminum conductors don't necessarily require oxide inhibitor. Okay, but again, if you want to use it, that's perfectly fine. The Aluminum Association recommends it. And we as a manufacturer of wire and cable, we're okay with it. It's not necessarily required, but you might have a situation where a piece of equipment does require it. And if it does, then make sure you follow the rules. Connectors are designed and marked for a range of conductor sizes. Let me tell you what, just because you've got a wire nut doesn't mean that you can twist all these conductors together and force a wire nut on it, okay? Make sure you know what your wire nuts, especially for grounding and bonding, and the integrity of those connections. Make sure you're not going outside of the scope or the range of conductor sizes for your connector, okay? Use proper compression tool if you're doing a compression style, okay? Make sure you're using a proper tool. Usually the dies that come with these compressions will tell you the same what you can have, and it's the same way for the connector with compression. It'll tell you how many can go in there per compression. Just make sure you follow the rules. And then a lot of manufacturers like Burndy will actually give you a color-coded dies that match their connectors for those connections, right? And here's a good example right here. So you got to do, like I said, make sure that you're putting them all in there, that you're not exceeding the number of conductors it can handle, whether it's designed for one conductor, two conductors. Make sure that's the way it is. These sometimes get pre-filled with oxide inhibitor, but just make sure you're using the proper crimping tool in order to get the job done. And usually just go to the manufacturer of whatever compression connector you're using and you'll be done. This doesn't mean you grab these here barrel splice and then you grab your side cutters and you just squeeze it tight. No, it's not what we're talking about. All right. Methods that are not permitted, 250.8b. Connection devices that depend solely only on solder are not permitted. Okay, now you can solder, but you can't be solely committed, okay, to just solder, right, to that connection. So you typically would pre-twist, and that would provide a mechanical connection prior to soldering, right? Now, if you're solely relying on soldered connections, they could be cold solder. They could come loose under heat cycling of the load through a conductor. Something can happen. They could pop loose, and then you open the integrity of your effective ground fault current path, right? So we want to make sure that we don't rely totally on soldering itself, okay? Solder conductors can fail due to heating as they carry current. Obviously, could get very high amount of current, can cause a termination to fail or a connection to fail, okay? Talking thousands of amps for a split second could cause a connection to blow apart if it's relying totally on solder. Also see 250.148E for restrictions of the use of solder for connecting equipment grounding conductors. Okay, so make sure you go check that out for any restricted limitations that you might have. All right, now 250.10, protecting of ground clamps and fittings. So I'm going to put a ground clamp in. I'm going to put one of those acorn clamps on a ground rod. Okay. It says ground clamps and other fittings exposed to physical damage are required to be enclosed in metal, wood, or equivalent protective covering. How many times have you seen a ground rod outside not driven down into the earth like it's supposed to, right? 8 feet in contact with the earth, but it's just sticking up. Okay, well, we'll say it's a 10-foot ground rod, and they do have 8 foot in the ground, but they left a foot up for whatever reason. If that ground clamp is on it, then it is exposed to physical damage. You're supposed to protect it. When I first moved into the house I'm in now, I went right out to the ground rod, because I'm a nerd like that. I went right out to the ground rod, and it was a little above grade. Nobody in the comments say, did you redrive it? I'm not going to answer that. I plead the fifth. And what it was just spinning around because the lawnmower kept hitting it and it knocked it loose, right? So it was subject to physical damage, being knocked loose, so it has to be protected. Easiest way to achieve that is to drive it below grade. Don't have to worry about it. Keep it below grade. Connections of ground rods that are above grade are particularly susceptible to damage and should be protected in some way. In some states, the inspectors will make you put a protective cone over it. I've seen other states where they make them put PVC over it down to a certain, and they'll put a cap on it, okay? Like a plug cap on it. And they'll put it in the ground, so that protects it. So you've got this ground rod, and they dig around it, and then they put a piece of PVC over it, and they glue on top of it like a clean out on the end of it. And then they put that around the dirt around it. So if it's going to stick out, that's a retroactive type of thing they can make you do. I just go out there, take a piece of PVC, Schedule 80, clean around the ground rod, put that in the ground, cut a piece about that long, put it in there, glue a clean out to it, and then put this clean out stop onto it. Whatever I need to do in order to protect it at this point. And then that makes them happy, okay? Also, it's an impalement risk, and you don't want that to happen either. All right, clean surfaces. We only got 2 slides left, and we'll be done for hanging in with me. I know there's only 9 people left, so y'all have hung in there with me, but I didn't feel like we should stop. And O just urged me on, so I had to go. All right, 250.12, clean surfaces. And this is when you're making connection to cabinets, enclosures, maybe it's baked on, or maybe it has paint on it or something like that. Here's what it says. Non-conductive coating, such as paints, lacquers, and enamels, to be removed from threads and other contact surfaces to provide good electrical continuity. Now, you could have a lock nut that actually is, there's 2 different types of lock nuts, right? There's the flat ones, and then there's the ones that have a bit of a hook bill on them. Those are designed to cut into the actual cabinet, okay? Now that's going to make a connection for you. But this is reminding you that if you have any type of paint or anything on your threads, you got to clean it off. We need that metal-to-metal contact. We need everything to be intact. Remember, we need that low impedance, intentionally constructed, effective ground fault current pad. Now, connection by means of fittings designed to make such removal unnecessary. No fittings are listed for this purpose, by the way, but you could, if somebody comes up with one that says, okay, well, you don't need to, then you can get away with it. But I will tell you that you can make metal-to-metal connection, and you have a lock nut, and if you're doing rigid, for example, and you're doing this, say, feeder applications, not at service, but feeder applications, then you can get lock nuts that will bite into the metal, that type of thing. And it will be evident when that happens. Okay. And of course, paint is an insulator. We need to make sure that we're going to integrity of these connections. We need to remove the paint where necessary to make these connections. Now, commercial applications, most of the stuff is stainless steel anyway. It's not painted. It's just stainless steel. Okay, well, then you're good to go. But you need to make sure that whether you're doing it in a residential situation, whether or not the painting or the enamel or that's on that cabinet or whatever is conductive. If not, then you might have to have jumpers, or you might have to have things if somebody wants to argue that point. All right, lock nuts. We're going to end up here. 2 general forms. You see how they look right here. You have the cut, which is punched from flat stock, crowned. Well, it's kind of crowned. It's threaded, tabs or ears, bent and left sharp. Okay, so it's got a little bit of point on it. And then you got these that are cast, and these are cast from iron, aluminum, zinc, or other material. and may have relatively flat surfaces, they are not going to bite into any material. So it's going to be even more imperative that you make sure that you get rid of any paint or surfaces that are non-conductive. Whereas you might have a lock nut that actually will bite down into the material and tie that threads to that lock nut, to that fitting, to that raceway, tying everything together, give you the best chance of clearing an overcurrent on a fault condition, right? All right, in summary, we made it to the end, folks, the 9 of you that are still with me. How do performance goals in 250.4 relate to prescriptive rules in the remainder of 250? So we have rules in 250 that's like the prescription on a bottle. Follow the rules. If you follow the rules, then you're going to meet the performance rules. You with me? I'm all choked up now. See what y'all have done to me? I do have coffee, by the way. And it is cold now, and I hate cold coffee. All right, number 2, requirements about objectionable currents over grounding conductors. We went extensively over that. You should know that now. Number 3, connection rules for grounding and bonding equipment. We talked about the different types, the 8 types of connections you can make, the importance of those connections. We even talked about low impedance, effective ground fault current path and why that's important. And those connections are vital to that taking place as well. And then lastly, we talked about ensuring clean surfaces for all connections, especially where anything that looks suspect. Clean it off, okay? It ain't nothing for you to have a little Dremel tool, rechargeable, and take a little end on it and just zzz, clean it off. Make sure. Now, if you got lock nuts that bite into it, okay. But you want to make sure you've got those clean surfaces, okay? All right, that's it for that. We'll come back to me, and we'll end this thing. Woo! Gosh, that's a lot. I don't know, y'all that made it through that, and even at a 30,000 foot view, that was a lot of info, and I appreciate you all. So the next unit we're going to be getting to is going to be talking about system grounding. So we're going to start jumping in and talking about alternating current systems that are required to be grounded, those that are permitted to be grounded, and those that are not permitted. And we're going to work our way through that. If you're in our grounding and bonding series, then it is Unit 2, and you can get a lot of extra detail there. If you want information on our grounding and bonding, it's called the Purple Fast Tracks, then just go to our website, electricalcodeacademy.com, and you'll see it there on the screen. Click on it, and it's one of our most amazing programs. The grounding and bonding is just, everybody needs to have a better understanding of grounding and bonding, and there's a lot of illustrations in there, even more than I've shown tonight. So it's great. Okay. All right. Well, folks, I kept you longer than I intended to. God bless you for holding in there for me. I appreciate every one of you. You've made Electrical Code Academy a success, and it couldn't have been done without folks like you. So I appreciate you listening. Be sure to subscribe on all of our platforms because we got a lot of stuff coming, and I'm excited about our new facility and all the things that we're going to be doing for you. Okay. So till next time, folks, stay safe. God bless.